this pattern comprises is about numerical properties of adjoint divisors. In so many different situations, birational geometry has to do with the relation between numerical and more geometric properties. So especially we usually like to turn something numerical which comes maybe from 3, you like to turn it into something which is geometric. So we have seen examples of this so many times before. Let's keep the notation of before K is algebraically closed and the characteristic of K is positive. So first, let me remind you of a resulting characteristic 0 over complex numbers. Suppose that x a plus b is a KLT pair. Projective, and here a is a and b are both effective, and a is ample. So ample, of course, it may not have integer coefficients, but maybe rational or maybe even real. Now, assume that the divisor L that we have seen so many times before. So this is what I mean by an adjoint divisor. This kind of divisors are called adjoint. Adjoint simply means that you have the canonical bundle and you add something to it. So that's what they call adjoint. Now assume that this divisor is math. Then one of the most important theorems in so I should assume this is over complex numbers. Over complex numbers or anything of characteristic 0, then one of the most important theorems in birational geometry over C says that L is semi-ample. And I guess you already know why it's important for this to be semi-ample, because we need this to run the minimum model program. So if you remember lecture 2 or lecture 3, maybe you see that we have this kind of divisors. We like to show they are semi-ample because we need them in order to run the minimum model program. So in a way, this is one of the really most central results in birational geometry over complex numbers. But now the same exact statement is expected to be true also in positive characteristics. But there are very few special cases of this theorem now. So we expect over K, yeah, remember this, characteristic is positive. So we expect it also to be true, but so there are some results in dimension 2, essentially this is true, and then you have in dimension 3, there are some partial results that I discussed in lecture 3, but in higher dimensions there is very, very little known, but however there is one particular case of this statement that was recently proved, and this is the main theorem of this lecture. This is by Kashiri, Tanaka, and Shu. So suppose that we have exactly the same kind of situation here. Suppose we have x plus p, this is projective, but instead of KLT we replace with something positive characteristic. So the similar notion would be strongly F-radial. So this is almost saying like this is KLT, but it's a little bit stronger than KLT. And as before, A and B are effective, A is ample, and let's say L is K plus A plus B. So in this theorem, I say that if the L is NF is just a numerical kind of additivity, then it should be semi-ample. Here, the theorem is in a way much weaker. It needs a much stronger assumption on L. Assume that L is strictly NF. So this doesn't just say NF, but strictly NF. Let me tell you what is strictly NF. So a divisor D is strictly NF if intersection of D with any curve is positive. So in the definition of NF, intersection is more than or equal to 0, but here we assume that it's strictly positive. So in other words, this divisor intersects every curve positive. It looks like an ample divisor. But in general, this kind of divisors, they don't have to be ample. They might even have negative for their dimension. In other words, they will not have to be any sections. So this is a very strong condition. If you have this condition, then the semi-ampleness holds. But because of this strict NF-ness, semi-ampleness in fact is the same as ample. Then L is semi-ample. Let me just say semi-ample, but this is in fact the same as ample in this situation. It's the same because it is semi-ample and then it cannot be trivial in any case, otherwise it just contradicts the definition. So it means that the ample, semi-ampleness just gives you the variety itself, so it should be ample. Okay, so for much of this talk then I will try to explain the main ideas of the proof of this theorem. For the reference you can look at the paper by these three people. But there is, in fact, almost all the ideas in the proof come from an earlier work of Tanaka. So I think the paper is called Freeness and Semi-Ampleness. Oh, really very ampleness. Ampleness is positive characteristic. So it's easy to find it on archive. But actually the paper was withdrawn because what he wanted to show, it turned out to be wrong. But the same exact ideas will be seen. Okay, so the proof is kind of a little bit, in fact the ideas are quite simple. I will try to explain, but there is a lot of notation and so on. So I will not try to give a precise proof, but rather I will try to be kind of very intuitive, vague, but just tell you what the main point, what the key idea is. If you understand that, then you will have no problem understanding reading the paper. Okay, so first let me mention one corollary. Why you should care about this theorem, although it's much weaker than what we want. Well, the main reason is the following thing. Suppose that we have XB, this is strongly rectangular, for example like KLT. Suppose that now G is an ample quantity of QT1. So again, it's projected. Now, let's define the following numbers. Suppose that lambda is equal to the infimum of all the now negative numbers, such that K plus B plus T times this G is net. Again, if you look at lecture 2 where I was trying to run minimum of the program for surfaces, you have exactly this kind of divisors. You take essentially the limit and then you try to show what you have in the limit is semi-ample. However, one important thing that we like to have is that, so if lambda, then the statement is that lambda is a rational number, and if lambda is positive, then there is at least one curve such that k plus b plus lambda g will be trivial on this curve. So this is again one of the main theorems coming from the rational geometry of a complex number. It's called the rationality theorem. So the reason it's important is because when you start with something arbitrary of this form, then you try to add some ample divisor, and then you form this limit. So this guy will be nil just by definition. Then to run the minimum model program, we like to show that this is semi-ample. So this is the kind of L we have here. Okay. However, it would be much easier if you already know that lambda is a rational number. If it's a real number, then things become a lot more complicated. But if you know this is rational, then at least you know you have a Q divisor. Sorry, so this B should be a Q divisor. But the G is, let's say, just cast here, or we'll take any ample Q divisor. So if you know that the lambda is a rational number, then everything here is rational, and so it's, as I said, it's much easier to work with, in a sense, with rational numbers, rational divisor, because you take some multiple and it becomes Cartesian and so on. So that's why it's important to show that this lambda is in fact a rational number. So the theorem says that if it is not equal to 0, then it divides that must be trivial at least for some curve. So this corollary follows pretty easily from the theorem. So we can assume that lambda is not equal to 0, otherwise there is essentially nothing to prove. So suppose that lambda is positive. Now, if there is some curve such that the intersection number is 0, then for trivial reasons, this implies that lambda is rational, and then we are done. So this is by the theorem. Sorry, you don't even need a theorem. If there is such a curve, then trivial lambda is rational, because these are all Q divisors. You calculate the intersection number, it gives you lambda to be a rational number. So all you need is existence of this kind of C. Now, if there is no such curve C, then this means that L equals to K plus B plus lambda G is strictly net. Because it's positive on every curve. And now the theorem says that this should be ample. But if L is ample, that means that you could in fact take even a smaller number here to get this net condition. So this will contradict the definition of L. Just cannot be ample, otherwise you could choose a little smaller number, smaller than lambda, with the same properties. Therefore, there must be such a curve, and then from that you will get that lambda is rational. Okay, so that's a trivial corollary from the main theorem. Then, as I said, I will try to explain the proof of the main theorem, but I will need some preparation. So I will try to explain a little some general kind of abstractions which in fact come from complex geometry. So first let me explain singularities in linear systems. suppose that x is normal and projective, and suppose that we fix a point, let's say closed point in x, and suppose that we also have some Cartier divide. So when you are given a Cartier divisor, you can look at the linear system of this divisor. Essentially, this means looking at the sections of this divisor. So the linear system usually denoted in this way. This just is the set of divisors. Effective divisors are the linear set. So in other words, you look at all the sections of this divisor. When you change the sections, it will give you different effective divisors. This is just so every section more or less corresponds to one of the divisors, but not exactly the one-to-one way. Okay. So this is the notion of a linear system, and then so the intuitive idea behind this is that if M is very positive, for example, if very ample and so on, you could choose one of these D to be very singular at this point X. So that's the intuitive. Vaguely. So roughly speaking, if the linear system is large, so by this I mean if you have a lot of sections, then you can find that there is such a T above such that T is very singular. At this given point X. So maybe I will give you one example which quite easy to see what is going on. You could just look at the projective plane and take the M to be the sum multiple of a hyperplane. So for example, you could just consider the case when X equals T2 and M is the L times H, the H equals the hyperplane. And then L is some maybe large number. So let's draw a picture. Then you start with this H, and then you have L times H. Of course, this is still kind of smooth in a way. It has some multiplicity, but it's not. You could not call it maybe so singular. But when the L is large, you can always, let's say this is X. I mean, X may not even belong to the original M, but you can always choose divisors in this linear system which will have very large multiplicity at this point. And this just comes from the fact that you have a lot of sections. I will now explain why you can get this if you have a lot of sections. Well, let Mx inside the local ring be the maximum ideal. Point, then we have a natural map from the sections of this line bundle to OX. So this itself is given by comes from the fact that you have a natural map to the localization of this line bundle at X. But this is isomorphic OX. So you fix one such isomorphism and then you will get one of these lines. So anyway, if you are more familiar with algebraic geometry, every section here is essentially a rational function. The rational functions will determine an element of the local ring. So you can think of it as rational functions. In fact, you can write it down as all the rational function, let's say alpha, such that the divisor of alpha plus m is defective. So there are many different ways of thinking of this. Either you can think of these elements of rational functions, they will then naturally give you something in the locally, or you can just think about it in a more abstract term. If you have any sheet, essentially, then you have from the section you have a natural map to the localization there, and then because here we have a line bundle, it will give you an isomorphism, and then you get this map. Okay. Now, for the moment, let's fix some number, let's say 1. Then, if you divide m, let's say mj over mj plus 1, this is a k vector space of finite dimension. So the idea is to look at this filtration essentially. We have mix inside mi minus 1x and so on until you get to mx and finally 4x. So you have a filtration of this form then. Naturally, and then when you look at the quotients, they have vector spaces over k and they have certain fixed finite dimension. Now, so from this map, if theorem is large, so this is just the dimension of this space, is large enough, then this remark tells you that there must be some alpha here which maps into this m to the I. That's pretty much saying that you have this section and it vanishes at that point with a very high multiplicity. So it implies that if you put G to be the divisor of this section, this is very singular. At the given point X. And so the picture I was drawing here is exactly, this is just the intuitive picture of such an abstract kind of argument. So that's singularity in the linear system, and then I'll tell you why we actually care about this kind of singularity. So now we come to creating singularities. A given point. So this is a general framework for producing divisors which are very singular at the point, but what is relevant for this lecture is the following setting. So suppose that X is again normal projective with fixed point X. Assume that L is left here, assume that A is ample and Caucher. So the Caucher condition later we will remove it. But for the moment we have this set. So assume that this L is not numerically trivial. Otherwise there is not. Then by the Riemann-Roch theorem, you can calculate the dimension of this divide. So if you choose the A to be ample enough, you calculate its section, the Riemann-Roch will give you just a polynomial expressing in terms of its section number, and then this will go to infinity if m goes to infinity. In other words, when you take the m to be very large, you in fact have a lot of sections. have a lot of sections is exactly what we need for this kind of step. And here we use the fact that L is not directly trivial, otherwise you don't get this. So we try to find divisors in the linear system given by the divisor here so that they are very singular at the point X. So by the previous remark, there are divisors linearly equivalent to M times L plus A such that this D has very large multiplicity. At the given point X. Now, assume for a moment that there is some curve C such that L intersection with C is equal to D. Then the intersection of D with C is equal to A and C. See that the intersection of A and C is a fixed number here that doesn't depend on the M. So no matter how large M is, this intersection number is exactly the same when A and C are fixed. Maybe I just have to on the picture here. Suppose that this is C and we are looking at the divisor. This is D, this is the point. Let's also assume that X is inside this curve. So the point X is the point on the curve, and then you have a divisor with very large multiplicity here. But if you have a curve, and if you have a divisor which does not contain the curve, and it has very large multiplicity, the intersection number should be very large. So there is only one case where it does not hold, and that's exactly where the curve is inside the divisor D. C is not inside D, then the section number should be very large. So this will be much larger than A intersection C. But that will contradict the default. So in other words, there is only one possibility. Therefore, C must be inside D. So in other words, when there is such a curve and you are given this point, you can create very large multiplicity at the point, but the problem is you can never avoid the curve itself. No matter what D you take, the D always contains the C, and this is not very useful proving the kind of theorem that I mentioned. However, if there is no such curve, such C, so for instance, if L is strictly net, then in fact you can create divisors with very large multiplicity. You can also avoid whatever subrank you have. Then there is D above which avoids any given variety, let's say V, which contains the force. So maybe I again draw a picture. Suppose that this is S. Suppose that we are given some variety V. Now I'm saying that if the L is strictly net, you don't have this triviality near the point X. You can always find. Just draw something two-dimensional. Then you can always find a divisor D, which will have very large multiplicity, but so that it does not contain the V. And then I tell you why we like to have this kind of picture. So in particular, can find D1 and Dn, they're all, the di's are all linearly equivalent to ml plus a such that every di has a very large multiplicity at x, and such that this is not the case for any other points, such that di has large multiplicity or singularity at a given x, but not at other points near x. But points here you need to understand in a scheme theoretic sense. So again, I better come back to this picture. We have here x, we have so what I'm saying is that we can create, let's say, very large singularity. This is D1. Use some colors. So let's say you can take, but in this case dimension is 2, so I need only one other divisor. I'm saying that you can take also something else, and so in this picture actually you could assume that near x everything just looks like smooth. There is no singularity, but there is only one here with very, very bad singularity. So if you go on a threefold, the statement would be you have three divisors intersect at that point, and every divisor has very large multiplicity, but then multiplicity along a curve is not as large as the point. So actually the best way to understand it is if you have some familiarity with complex birational geometry. So, for example, if we work over the complex numbers, then what we have is that if t is equal to the low canonical threshold at that point, then the statement is essentially that if you look at this pair, x t times d1 plus d, and this will be precisely low canonical at the point x, but it's KLT everywhere else. So in other words, you get a pair which is precisely low canonical at that precise point, but when you move to any other nearby point, it becomes KLT. So in other words, the deepest singularity will be concentrated precisely at that point. But we don't really need this. You don't need for the proof of the theorem, but if you are familiar with this statement, then it's easier to understand. Okay, so I have already talked about these things, and then I will give you the sketch of the proof of the theorem. Okay, first let me remind you of what is strongly F regular and so on. So recall that x delta is a pair, then we say that this pair is we say that this is sharply as pure. This comes from lecture 4. And the trace map the trace map, which is from Fe lower star 4x minus t to the e minus 1 times k plus delta, and then you have to round it up. So you have a trace map to OX, and we say that this is surjective at the point x. So in lecture 3 at some point I wrote this trace map, but in fact when I Again, the definition is slightly different because more defined in this form. So you just need to remember that this shift here is in fact just Fe log star OX E minus 1 times delta and then OX. And this one is just OX. So these are given by duality. So you can define this notion of sharpness pure using that by looking at this shape, or you can use the duality of this diagram to say that you want some subjectivity. And strongly and regular is a bit stronger than sharply and pure. So these notions are, they in fact play an important role in the proof. It's not just for the sake of the statement, but in fact the proof uses very precisely this definition of sharply and pure and strongly and regular. Okay, so, but we say that the pair is strongly and regular. So, that there is some key to this. But strongly and regular asks that for any effective divisor, let's say E, and there is one of these numbers, E such that the trace not be the subjective, but you need to take into account its effective divisor. So you must have subjectivity of the trace map precisely again at that point, but this is a bit stronger than sharply pure because you are also adding. So here in this picture you are removing also something. So in other words, you have subjectivity of the trace map after even you remove something. Okay, let's go back to the proof and see how works. So as I say, the proof is not precise, not 100% correct, but just I'm trying to give you the idea. Well, first, for simplicity, let's assume that A and B are both, so this is L, everything Q divided. If they are not Q divided, you have to use approximation by rational divisor, and this will kind of, it's a very well-known technique. Let's just remove that and assume that everything is rational. So we can choose some fixed number L, maybe large enough, and we can take divisor Pi linear to now L times ML plus A. So the thing is that the L and A are not Cartier, they are rational divided. That's why I'm taking the L. So I just multiply by something to make everything integer coefficient. So this will be Cartier divided, then I can apply this creating singularities. So actually we better also take fix some points close points. Then I take these divisors which are effective, they come from the linear system of this ML plus A, so the M probably is something quite large, such that the DI are very singular at the point X, but as I explained, not at other points nearby. So these are chosen exactly just like in this picture here. So I'm taking all the divisors so that I have a very large multiplicity concentrated at that exact point. Now, let's take W to be the intersection of the V1 of N. So you can assume that the divisors don't have any common component, and that so that it becomes a zero-dimensional object. However, this is not just a point, it has a scheme structure. When you intersect all these divisors, you will have multiplicities, and then this is what is called a fat point. It's a point, but it also has some non-reduced structures. But as far as the proof is concerned, the important thing is that it didn't focus, it's concentrated on one point. But it's actually also important to have it with a kind of large non-reduced structure that we will see in a bit why this is important. Okay, we could also change maybe the D a little bit for some more or less trivial reasons, such that P does not divide the index of Kx plus B. This is the same thing as saying that there is some E such that e to the E minus 1 times Kx plus B is a Caucher divisor. So this may not hold originally, but if you change the B a little bit using an ample divisor, this will be satisfied. Quite simple reasons. Okay, so we choose one of these E's, maybe very large. So for some simple arithmetical reasons, when there is one E like this, there will be infinitely many. So you can choose maybe something very large, and then put n to be equal to this divisor that we will see in a minute why I define this. Kx plus b plus t times d1 plus t times d2 and so on. So this is a divisor, but I'm assuming now that it is char t. But you have the t parameter here. For the moment it's not clear what it is, but we will see soon what t we should take. Then we have the exact sequence here. We have the exact sequence of this substring W. So we have a short natural exact sequence of this form, and then we're going to tensor the divisor with this short exact sequence and take freeness and so on. Okay, we have this short exact sequence. I have this Caucher divisor. I can tensor this and write. So I have OX and tensor with the ideal shape of this subscheme. I have the OX, and then I have for W. So this is good. Tensoring by OXN. But this is not precisely what I want. I want also to take the image by the frobenius. So because the frobenius is a finite map, when you take the image, you still have the short exact sequence, and then we have also downstairs we have another natural short exact sequence corresponding to the closed point x. This is the ideal shape of x, and then you have another short exact sequence downstairs. Now, by the trace map, we also have a map given from this shape to OX. This is just the trace map. And of course, this trace map, when you compose it with this injection, it will give you also a map here. Let's call it theta. So far, whatever I told, essentially, not really much characteristic fitting it, probably work or every field complex number, whatever. This is where the characteristic fits are coming. This is where the main idea comes. So you have this trace map here, you get this map there. This is surjective bias. So we can change T so that this is surjective. So we can assume this is surjective. This just depends on what T you take. If the smaller the T, the more chance you have for this to be surjective. So I'm essentially taking the largest possible T. If you take the T to be too large, you may lose this condition. But for the moment, I take the T so that this is surjective. So this will give you a condition essentially on the number T, which appears inside F. Okay. Now the very key idea is the fact that if you take the T to be larger, like as large as possible, then because at the point X everything is so singular, very clear picture, but everything is so singular, then there is no more room for adding anything else. If you add anything else, you lose this condition of the singularity. So again, if you are familiar with complex geometry, it would be very much easier to understand. If you have this precisely low-canonical singularity, you cannot add anything else. If you add any, even epsilon, you will go out of low-canonical. You will fall into a larger, deeper singularity. So if this is precisely low-canonical, there is no room for adding anything extra. That's pretty much what we are doing here. I'm taking the T to be so large enough, I'm taking the divisor to be so singular that if I add anything else, it will not be sharply acute. So you need kind of some balance here. So since the PIs are very large, or maybe I better say just by construction. So I will repeat. By construction, so there is no more room to add, so that to add object of, actually in this case the W itself is not a divisor, but to add maybe subskin to keep the trace map surjective. So in particular, because the W is just a point, but it's kind of fat, it also has a large multiplicity. Here, the answer is like saying you are adding W to this feature. Of course, W is not a divisor, maybe not so easy to understand. But you can think of it for a moment, maybe just like a divisor. If you add the W here, the subjectivity will fail. So in particular, it means that theta cannot be surjective if the T we have chosen is kind of maximal. Maximal to have the trace map surjective. Yeah, so all these creating singularities and so on is essentially for saying that here you have subjectivity, but there you don't have. And so this is a local ring. If the map is not surjective, it has to map into the maximality. So we have then a larger diagram of this alpha. So the image of theta is inside mx, and this implies immediately that there are alpha and theta making the diagram commutable. Now, by assumption and by construction, this map here is surjective, so I'll write it in this form, and that by definition of this kind of short exact sequence, this is also surjective. So you have a surjective map followed by another surjective map. This implies that the beta here should be surjective. So the beta is a composition of two surjective maps. The beta itself is also surjective. So this is, you have a sheaf on W, but the W itself is concentrated at one point. It's an affine scheme, and here you also have that one point which is affine. So if the map is surjective at the map of sheaf, it's also surjective at the global section. So in fact, this is surjective. Since W is affine. Now, for one moment, assume that H0 from here to there is also surjective. Then that means that H0 from here to there is surjective, and so H0 from here to there will be surjective. But for the moment, of course, this is not useful. I need to tensor with my net divisor. Then I could say that there is some section here which leads to a section here. So I need to actually write down the following diagram. So consider the diagram H0 essentially comes from here, but I also tensor with some other divisor that I need. So I have H0 as low as star or x. I have n. I'm adding n times, but n is some fixed number, and then I tensor with NPL. And then I have a natural map to W pushed down by Frobenius, or W you need to tensor with again with n EL. Then you need to tensor also downstairs. You have H0 that's 4x. Here I have n times L. So the reason here you have NL, but here there is also P, just because you are applying Frobenius when you go upstairs. You have P to the E times whatever you multiply. And then finally here I have H0 Kx tensor with 4x and L. But again, this guy is surjective. Just simply because it's essentially the same as this. So tensoring with something here does not really affect. So we are almost there. There is essentially one last bit. Okay, let's call this gamma and let's call it the rho. So I already noted it's surjective. If I show that this rho is surjective, it implies that gamma is surjective. But gamma being surjective exactly means x is not in the stable base locus, or in the base locus of n times L. So if rho is surjective, this implies that gamma is surjective. This implies that x is not in the base locus. L. So in other words, it means that L is free and L is a free divisor at that point. So in other words, NL is semi-ample, or L is semi-ample at this given point X. But the X was chosen to be arbitrary. So you apply the same argument at every course, it shows that n, in fact, the L is semi-ample L. So the only thing remains to show is that these guys are subjective. And the subjectivity comes from just a simple vanishing step. So we only need to show, that H1 of S equals star or X n plus n L if the tensor equals by W, this is going to be equal to 0. So if this is not sequence, you have H0, you have H0, the next step is H1. If you show H1 is trivial, then you get subjectivity. And as I said, this comes from vanishing, so you only need to see what this divisor is. So now remember that n plus NCTL, this is the same as minus e to the e minus 1 times f plus b plus NCTL, and then you have something that we have added. We need to remove that also, so this is 2 times 1 plus n. So this is just by definition. And now the whole point is that this divisor is quite ample. Very ample. Maybe very ample is not a good word. It's quite ample. But more or less it's the same. So the point is ample. Sorry?
Sufficiently.
Sufficiently ample. Yeah. I didn't say very ample because we need to be careful about coefficients. So the point is that here I didn't use A. The A is missing here. But the L, original L, of course, contains A. It's K plus A plus B. So you see that. So if you take a very large multiple of L, let's say R times L minus, so I will not do the calculations here, but just try to explain it. Here, let's say A times L, and then you have minus B times A plus B. What you are left is with this A minus B times L plus A times B times A. So this guy is anyway the net divisor we started with. This is ample. Now, if the B is large enough, this will be, in fact, will be very ample. It will give you a lot of positivity here. So that's why I'm saying that this is quite ample. In fact, it's very, very ample. And so the only thing to note is that this divisor here does not cause problems. But by the way, by construction, the T is kind of relatively small. That's because these divisors were so singular at the point, you can only add a little bit of them to, let's say, to keep canonical or to keep sharply FQ. So this threshold should be kind of small, it cannot be very large. So even though we are removing this divisor, but in fact if you write this down just in terms of B and A and K and so on, this does not cause much trouble. You still have a lot of positivities. So we have enough ampleness to get a vanishing statement like this. Because the W is anyway the fixed sub-scheme. If you have enough ampleness here, this H1 is going to be equal to 0. So everything is really concentrated in this diagram here. Where is the diagram? Okay, here. Because I didn't tensor still. If you, after you tensor it with and L, then everything will be inside this diagram. You are using this true subjectivity here. This is conditional singularity. This is anyway naturally given. We are using the fact that W is affine, so you have subjectivity here not only as shield but also on the sections. And the other thing we are using is this positivity of H1. And that's exactly given by the fact that the trade morphism already will leave you with some positivity. It will leave some ampleness inside this divisor, and then you can use that ampleness to get vanishing, and so that at the end you leave sections. Okay, I will start.
Any questions? So the condition that is strictly net is used to create this only singular point.
Exactly. That's the role of strictly net. As I was trying to explain, it is not strictly net. All these divisors will contain many others of varieties. So even you create variable singularities at the end, you also have variable singularities somewhere else. So, and if you have that situation, then this T here, you cannot maybe choose it small, and then the positivity here will disappear. Okay, I mean that's one thing, but another thing is that then you might fail to make this diagram symmetric. And if you don't have that situation, it might be subjective, and then you don't have the diagram.
Any other questions? Okay, let's speak learning.
So the next lecture will be the last one, and that's more for about 3 folds. Mostly I'll talk about physics.